In this video, we're going to continue our study of calculus and parametric curves and taking the derivative idea one step further to go from position to velocity and lastly now to acceleration. We're going to do this in the context of our circular motion, which is defined by cos of t and sine of t, so uniform speed around a unit circle. We've already seen how to get part of the way to our acceleration, and that's by getting our velocity. And we do that by taking the component by component derivative of our position. So if our position x coordinate is cos of t, the velocity x component is going to be sine of t. And likewise, the y component, position is sine, that derivative is cos, and that will define our y velocity. So we now have that tool in our toolkit that allows us to go from any position vector to a velocity vector. The visualization of this is also helpful. If we draw our unit circle like so, and add velocity vectors at particular times, let's say times 0, that's a good starting place. Our position is going to be cos of 0 and sine of 0, and that's simply 1, 0. We'll do this in blue to keep the colors consistent. The matching velocity is going to be, going back to the last page for a moment, negative sine of 0 and cos of 0, and cos of 0, and that's going to be the vector 0, 1. And so if we draw that out here, that would be our velocity vector, v of 0. Going back to our expectations, that matches the tangential nature of the velocity vector. If we're traveling in this circular pattern, at this instant, we will be moving directly upwards. We can do this at more exotic points as well. Let's go to, say, 5 pi over 4, just for variety here. And if we do that and find our position, we can run that through the cos and sine function, and that's going to get us down to this corner here, which will be negative 1 over root 2 and negative 1 over root 2. The matching velocity at that instant is going to be defined by negative sine of 5 pi over 4. And if you run that through your calculator, you're going to get a positive value once you flip the sign there, 1 over root 2. And when you do cos of 5 pi over 4, you're going to get negative 1 over root 2. And that vector happens to be exactly what we'd expect from the diagram here. It's going to be down at a 45-degree angle to the limits of this sketch, and again tangential to the curve and so on. So this is still velocities. Of course, because this is uniform motion and we're looking at the velocity vectors, the direction's changing continuously, but they will have the same length because the length of velocity vectors gives us the speed. And our speed is constant. For this particular definition of our position over time. Well, that leads us to the question about acceleration. If our speed is constant, we're not speeding up or slowing down, but we are changing direction somehow, how does acceleration play into this? And again, this ties into ideas about acceleration that you see in your physics class. We're going to formalize it here using vectors in mathematics. Remember that a second derivative of a vector-valued function, if the position function is what we're starting with, gives us acceleration. So position, two derivatives to acceleration. There's also a relationship to concavity, though. When you talk about first derivatives, you talk about slope. When you talk about second derivatives of graphs, you talk about the concavity. And what we're going to try to do is see how that plays out when we think about vector forms and how much of this we can still use. And it turns out it's quite a bit. So the second derivative of a position does measure how fast a particle is accelerating, but it also represents a direction now that we're working with vector-valued functions. When the acceleration vector points in a direction different from the velocity, it indicates how much or how strongly that curve is going to bend. If we imagine sketching that scenario out again down here with our unit circle, we have our velocity vector here. We know the velocity vectors at later time points. The acceleration is what changes the velocity, so rate of change of velocity. So if we have this as our velocity at time 0, and we have this as our velocity at time pi over 2, then there must be an acceleration that's bending this down so that our velocity changes and becomes something else. You can also think of it with a force idea, because forces are what cause accelerations. So in the absence of a force, we would continue in a straight line, but because there is a force resulting in an acceleration, we're going to move out of that straight line. Our intuition tells us that if we're having a stronger bend or curve, in other words, if we're going around a bend faster, or if we have to pull harder on something to get around that curve, and you can think about it as imagining yourself in a car following this trajectory, the more impetus you feel, the tighter the curve can be. Now we just need to formalize that with some mathematics.